Okay, and we can start. I will share my screen. This is a lection on this discipline theory of signal processing. And I will share my screen on the presentation that we stopped last time. Do you see my screen?
Yes, doctor.
Everything okay, super. Okay, and so at first, let's a little bit memorize what we did and what we considered last time. It was a lection that is called lection number 3, and it includes two main questions. It's Walsh transform and Hadamard transform. Actually, we started with control questions concerning the material of previous lection, and then we started considering Walsh spectral transform. The main things of this method is that firstly, it is operating with the basic function that take a value as +1 and -1, nothing more, only +1 and -1. Of course, it's very simple. The set of function consists of 2 in the power n values. It depends on the number of discrete values in a signal that you would like to analyze. So at first, we should investigate how many discrete values are in the signal that we are going to analyze. And this number should be the power of 2. It is very important because in other case, it would be not possible to apply this method. So firstly, we should analyze initial signal and just count how many digits we have. And this number should be 2 in some power. Power could be anything, for example, 2 in the power 2, 4 numbers, 2 in the power 3, 8 numbers, 16, 32, and so on and so on. The main thing that it should be 2 in the power n in arbitrary power. And depending on this power and depending on the values, number of values in an original function, we should use different sets of basic function of Walsh transform. For example, here in the slide, we consider the set of 8 function. This set is suitable for the signal that consists of 8 digits. So if you have 8 digits of signal, we can analyze this signal using this set. There are 8 functions in a set, and each function is assigned by its 8 numbers. And every of these numbers is equal to +1 or -1, no any other values. And in each set of basic function of Walsh method, exactly 1/2 of this function is like cosine function, are the even function or pair, like we considered last time. And the second half is odd function, means non-pair, like a sine function. So if you have 8, so 1/2, 4 functions are even and 4 functions are odd, pair and non-pair. And the most suitable way of calculation of the spectra using this method is a matrix way, matrix form. So the set of basic function could be represented by the square matrix. And the dimension of this matrix would be the same with the number of discrete values in the original signal. For example, if you have 8, so our matrix will have a dimension 8 by 8, 8 rows and 8 columns. And each of the element inside this matrix will be or +1 or -1. No any other values could be. And did we consider an example last time? Do you remember or not? Because I'm not sure. Could someone say?
Yes, I think, doctor. Yes.
So we considered it, yes?
Yes, yes.
Okay, so we considered already this matrix. Here is this very simple matrix 4 by 4, only 4 function. It means 4 horizontal rows in a matrix. So the original signal here, it is marked like x from n. It's our original function. And you can see that this original function, this original signal contains 4 values. So if we just count it and we see that there are 4 values, so we should use the matrix 4 by 4. Okay, and we did it. Actually, it was not so difficult. Now I already remember that we considered it definitely. And we obtained a result. This result will be the Walsh discrete spectrum. And because original function contains 4 values, so its spectrum also contains 4 values, the same number. It's always so, it's a rule, that how many values do we have in a first original signal, exactly this number of values will be in a spectrum. So if we had original signals that consist of 4 values, then our spectrum will be also consist of 4 values. And here, these 4 values, X capital, if we see a capital letter, we understand that this is spectrum digits, and numeration, numbering of these digits is from 0 till 3. X from 0, X from 1, X from 2, and X from 3. Also, it could be an inverse task when we know the spectrum and we have to understand what will be the analyzed signal. Okay, so it's like inverse method, like any spectral transform. Walsh transform also has its inverse form when we, let's imagine that we don't know what is the original function, but we somehow just know what is the spectrum. So we try to find the original function for using just known values of the spectrum. It means that for direct transform, we know original function x small from n, and using direct formula, we obtained x capital from k. This is a spectrum. And inverse transform, we know x capital, and we are trying to find original function x small. And here there is very easy in this method because this method is symmetrical, and we are lucky with this because we don't need to find out what kind of matrix we should use for the inverse transform. We use exactly the same matrix like it was in a direct transform, the same matrix like it was in example 1 when we calculated a spectrum. Here we use the same matrix and we use the values of spectrum 1.5, 0, 0.5, and -1, and we multiply them together. As a result, we obtain original function 1, 2, 0, 3. It contains 4 values, and we can compare it with original function from which we started this example, and this is the same. So our method is working. We just proved it. And now we see that really this method is symmetrical. It's not like any other, not like many other methods. For example, Fourier transform is not symmetrical. And we considered Hartley transform, it was symmetrical. So if we use the same algorithm for calculation of the spectra by known original function, and the same algorithm for the calculation of original function by known spectra, it means that the method is symmetrical. So Walsh transform is definitely symmetrical. We use the same matrix. And now we are going to the next method. Actually, there is not just a different method, but this is a modification of Walsh transform. I will explain you why. Firstly, it's called Hadamard transform. Hadamard, it's also the last name of the scientist, mathematician who invented this method and who proposed to use this modification. So actually there is the same transform that we considered, it's Walsh transform, but the order of basic function in the total set is different. So we just have to take the same function, but mix them and place them in different order in comparison with the Walsh transform. And if you consider it like a matrix, so the rows of matrix are the same, but they are in another order. This another order, I will explain you also about this, because there is not just arbitrary another order, it's very, very strongly understandable, strongly algorithm of this mixing. So rows and matrix are mixed somehow, we don't know yet how, but I will explain. And there are also only for this method, for Hadamard transform, there is a recursive algorithm of matrix forming. What does it mean, recursive? How to understand this? Actually, this is very easy because recursive algorithm means that if we know the smaller matrix, somehow we have a way how to build a matrix with a small dimension. And if you know this matrix, we could construct the matrix with a higher dimension. And then to construct the next one with an even more higher dimension, and so on and so on. So it is a very easy and logical way how to build a matrix with a necessary dimension. This is a recursive algorithm. When we know the previous element and we are able to construct the next one, and then the next, and so on. So we are starting with elementary matrix brick, something like a very small matrix, and it is really small, the smallest that could be imagined. It's noted like H. H is the first letter of the last name of the scientist, Hadamard. So the matrix is marked by the letter H with the lower index 1. This lower index indicates the dimension of the matrix. So if you have 1 here in the index, it means that only matrix 1 by 1. So actually, it's even not a matrix, it's just a number, but we consider it like an elementary matrix. And we will use this elementary matrix, this elementary brick, like a basis for construction of the bigger matrices. So using this H1, we will construct H2. And here is a very good illustrated the logic of the construction. So as you can see, matrix H2 index 2 indicates that we are dealing with the matrix that has a dimension 2 by 2, 2 rows and 2 columns. And we can see that the first row as well as the first column are consisting of only ones, only elementary bricks, because our elementary bricks is H1. So we put H1 like just a number 1 here in 2 elements of the first horizontal row, 1 and 1, and also in an element as an elements of vertical row, 1 and 1 here. The only place that remains, here we just take our brick and invert it. And we just write down -1 here in this only 1 remaining place. And this is the logic, because all other matrices we will construct using this logic. For example, let's go from the dimension 2 by 2 to the next level. It will be dimension 4 by 4. You should remember that we are going with the step 2 in the power something. So it was 2 in the power 0 equal to 1, 2 in the power 1, H2, and here 2 in the power 2, it's the matrix H with the lower index 4. And of course, this matrix should contain 4 rows and 4 columns. But how to get it? We should memorize that we use recursive algorithm. So using the previous dimension of matrix, we are constructing the next one. And the logic is here. It is illustrated in the matrix H2. So we just take the previous matrix and put it in a first row and the first column. So like here, using when we're constructing H4, we put the previous matrix H2 and just put it in the first column, horizontal column, and also in a first horizontal row, I'm sorry, and in vertical column, H2, H2, and here H2, H2, first row and first column. The remaining place we should fill with the same, but with the opposite sign. So we put minus H2. And then we can put instead each of these elements, it's like a matrix, yeah? So H2, it's 1, 1, 1, minus 1, and we should put it here, and here, and here, and also here, but with the opposite sign, with a minus. And as a result, we will obtain a matrix 4 by 4. The general formula how to use this recursive algorithm and how to obtain the matrix with the next dimension using the matrix with previous dimension is here. For the arbitrary order of 2 in the power n, we should use the previous order, 2 in the power n minus 1. But the logic, as you can see, is the same. Here, here, and here, we just repeat the previous matrix. And here, we also repeat it, but with opposite sign. How it works? For example, for the dimension n equal to 8, yeah, we could start forming the matrix with dimension 8 by 8, H with a lower index 8, using the same logic. So we know that we could construct matrix with the dimension 8 using the matrices of dimension 4. So we put it here 3 times without modification and 1 time with the opposite sign, H4, H4, H4 minus H4. Then we should open every one of these matrices. So we know that we could construct H4 using H2. So we just open it, and instead H4, we are writing H2, H2, H2 minus H2. So these 4 elements are the element of them are the whole matrix H4. Here you see that these 4 elements are just repeated. And here also they are repeated without modification, without changes. And here, this is the most interesting. These 4 elements are also the same, but every sign is inversed, as you can see. Where we have plus H2, we have minus H2 3 times, and the last element was minus H2, and now it changed its sign, and we have plus H2. But it is not a finish. We should keep opening the values in order to achieve the matrix with dimension 8 by 8, and the elements of this matrix should be only plus 1 and minus 1. We should memorize this, that for Walsh method and Hadamard method, we have a basic function that takes the values plus 1 and minus 1. We do it, we just open H2. You know that H2 is already consist of plus 1 and minus 1, like at previous slide here. Yeah, you can see it here. So we just open, we replace each H2 by these 4 elements. And we should do it how many times? 4 times in the first horizontal row, you see? So here is H2, again repeated, and again, totally 4 times in a horizontal row, and we obtain first horizontal row of the final matrix with dimension 8 by 8. We also do it with all other matrices. And just open H2 and minus H2 by, when we use minus H2, we should inverse all the signs, like here, 1 minus 1, no, not here. Yeah, 1 minus 1 minus 1 minus 1, yeah, like here. And okay, when we do this, we obtain the final matrix and we can use it directly. If, for example, we have some signals that is to be analyzed and that consists of 8 values. And here you can see a formula that could seem a little bit complicated. But actually there is not very complex, not very complicated. The only things why it looks like not so easy is that we should remember that we use like a binary system here, because the basic function here, it takes only 2 values. So we should represent a 10 from the decimal system. We should transform each number in a binary system. I will show you this on the next slide. And here in the formula, under the sign of sum, we have components in binary representation of decimal numbers of our 2 counters, n and k. So we should deal with the conversion from decimal to binary system and back. Here, let's go to the next slide. The same formula, just repeated for the better understanding. And here you can see how it was calculated and how we obtain actually the same matrix. So we can obtain it just using recursive algorithm. This is one way, but also there is a second alternative way how to calculate each element of this matrix and totally to calculate all elements. I told you that we should transform decimal numbers into the binary numbers. And for example, here only first 4 numbers that could be, because n and k, there are 2 counters and they are taking the values from 0 till n capital minus 1. And our n capital is 2 in the power n small. You should remember this. So we just put it here. It's only 4 numbers, but we can continue, of course. We can put it 4, 5, 6, and so on, as many as we need. And then we should transform it into binary form. So instead 0, we have 0, 0. We use just 2 binary digits because we have only 4 decimal numbers. So 4 in 2 is 2 in the power 2. It means we need only 2 binary digits. But if we would have, for example, 8 values, 8 is 2 in the power 3. So we need to convert from decimal system to binary system. We need 3 digits, not 2. But here 2 is enough. So we just represent decimal number 0, 1, 2, and 3 in a binary system. I hope you understand this very clear. And for example, you see that 3 is represented by 1, 1. So the next value will require additional digits because it could not be more than 1, 1. And for every of these values, for every combination of n and k, we could put these values, these binary digits, in a formula, because our ns and ks is this position, is these digits. As you can see, s is changing from 1 till n. In this case, It's changes from 1 and to 2, only 2 numbers, K1, K2. This is the smallest digit, and this is the highest. And here also N1 and 2, the lower digit and the higher digit. And here there is a combination NS and KS. For example, if you will take N equal to 0, and also N could be equal to 1, 2, and 3, but K is equal exactly to 0. So it doesn't matter what is N, because K is equal to 0. Because if we will multiply it by 0, so it doesn't matter what exactly we will multiply it by 0. Yes, the result will be always 0 in any case. So if K equal to 0 and N equal to any other, so we have a value of basic function phi equal to -1 in a power 0. It's equal to 1. Then if N equal to 0, it's an opposite case, and K could be different, absolutely. Again, we have the same, because it's also multiplication by 0, and the result also will be equal to 1. It means actually returning to the matrix. This reflects the fact that we have a first horizontal row and a first vertical column that are equal to, that contain only ones, not -1, but just only the same elements. Totally 8 elements, and all of these elements are equal to 1. So this is the first row and the first column. All others are calculated in a similar way, but here there is no more zeros. We have 1 and 1, 1 and 2, 1 and 3. Yeah, because N and K could take numbers, all the numbers from 0 till 3, and actually there are totally how many combination, and we can see it here. It will be 4 by 4, yeah, from 0 till 3, 4 different values for N, and the same 4 different values for K. So 4 multiplied by 4 equal to 16. So totally it will be, it is for the matrix 4 by 4, and there it should be totally 16 numbers should be calculated. Or another way, without calculation, just construction of the matrix, like here using recursive algorithm, the results should be the same. And now, very interesting thing is the connection between these two methods that we consider. I mean, Walsh method and the Hadamard method. Because in the beginning, I said that this is actually two modifications of the same method. And the difference between this modification is the order of the function in a total set. So the order of a horizontal rows in a matrix. And what is the law? What is the rule? How to place these rows in order to obtain matrix of Walsh and matrix of Hadamard? Actually, how to obtain Hadamard matrix, we already know. This is a recursive algorithm, like here, yeah? But for the Walsh, it's not clear. And here is an explanation. It's the slide number 14, and it is actually very interesting because it helps to discover how these two methods are connected with each other. And here we should use, it's already used, so-called Grace code. It's a binary code that has actually also different forms. But it's very well known. I would say even that this is a famous code. You can find more information if you need, just by searching the internet or literature. So the gray codes are very, very popular. You will see if you will interest yourself. Okay, so Grace code, what does it mean? The first thing, this is a binary code. So it contains, like any binary number, of zeros and ones. And the main feature of the Grace Grace code, for every modification of Grace code, actually we will consider only one modification. So the main feature is that if we if you're just looking for the consequence of the numbers presented in Grace code, and if you will have a look to the neighbor numbers, two neighbor numbers in a Grace code, so they will differ only in 1 digit. Only 1 digit will be the thing that is a difference between the neighbor values. And it will be also the same for every neighbor. So we just could take first and second and third, and so on and so on. So if they are placed nearby, if they are neighbors, so they differ from each other only in 1 digit. So all other digits are the same and only 1 is changed. This is the main feature. And the modification of Grace code that we will consider, because it has a connection to our subject, to our topic, it's a connection between Walsh transform and Hadamard transform. It's so-called reflective binary Grace code. So the key word here is reflective. Why it's reflective, why it's called so, I will show you. And actually you can see it by yourself when you have attentive look to this table in this slide. There are 3 examples of reflective binary Grace code for different numbers of digits. First one is marked by green color. It's a 2-digit Grace code. So this is a sequence of binary numbers where each of these numbers consists of only 2 digits. So we have here in the left side the normal binary numbers, not presented in gray codes, just binary numbers like they are going in a normal binary system, 0, 0, 0, 1, 1, 0, and 1, 1. So this is a normal sequence. But it could not be called Grace code because we know that the main feature of Grace code is difference in only 1 digit for the neighbor values. And if you consider to this value 0, 1 here, and the next one, 1, 0, so we see that the difference is in 2 digits, yes, in the lower and in the higher digits. So 0 becomes 1 and 1 became 0. So it could not be called a Grace code. So it should be modified in somehow. And here in the right side, you can see a modification. So instead 0, 0, we have still 0, 0. Instead 0, 1, still 0, 1. And here there is a difference. Instead 1, 0, that is not suitable for Grace code because 2 digits are changed and it is not admissible. We just take the last value, 1, 1. Because if comparing 0, 1 and 1, 1, we see that only 1 digit is changing, only higher digit. 0 becomes 1 and the lower digits remain the same, 1 and 1. So the next value in Grace code will be after 0, 1, 1, 1. And the last one here in 2-digit Grace codes will be 1, 0. Because if again we compare the previous one, 1, 1, and the next one, 1, 0, we see that there is only change in 1 digit, in a lower digit. So here is an example of 2-digit reflective Grace code. Why reflective then? Let's have a look to this consequence, and we see some rule. If you see attentively, we will note some rule. If we are looking to the lower digit, we can just divide all the set in two equal parts, and we will have two values under the line and two values above the line, here and here. And if you're starting from this line and going from this line to the side, so to above and to the top and to the bottom, we will have the like a reflection. Here 1 and here also 1. Here 0 on the next step and here also 0. And now I'm talking only about the lower digit. 1 0 and 1 0. So the more far we are from this central line, then we have all the reflection in the upper part and in the lower part. And then let's have a look to the higher digit, and we will see that above the line, all higher digits are equal to 0, 0, 0. And under the line, we have only 1, 1, 1. The same rule you can also observe for 3 digits and 4-digit Grace code, and even more. I just didn't represent it here because I think now it should be clear. For example, if you have for 3 digits Grace code, first thing that you can observe is that if we take any two values that are placed nearby, so any two of them are differ from each other only in 1 digit. For example, 0, 0, 1 here, and the next one, 1, 1, 0. The difference is only in a second digit. All two others are equal. If you take 0, 0, 1, 1, and the next one, 0, 1, 0, we also see that the difference is already in the lowest digit, but still in 1 digit. And also the rule about reflective binary code. So again, we just divide all the set on 2 halves and by some imaginary line. And above the line, all digits except the highest one will be reflected. So for example, for the middle digits, we have above the line, starting from the line 1, 1, 0, 0, and to the bottom 1, 1, 0, 0, the same. It's like a reflection. And also for the lowest digits, 0, 1, 1, 0, and here 0, 1, 1, 0. As regards to the highest digit, so on the line, all these values are zeros, and under the line, they are equal to 1. So for highest digits, it's another rule, but also there is the same for 4-digit Grace code. Here is the same explanation in a text. Reflective binary Grace code is the first half of values during the reordering reflects the second half without considering the highest digits. And the highest digit is to be just inverted. So it was zeros in the upper half and it became ones in the lower half. So it's like a feature of self-similarity or self-reflection. That is why it is called reflective binary Grace code. Okay, and we can try to apply this rule for the Hadamard matrix with the dimension 4 by 4 of the order 4. And how, just returning to the method of Hadamard and Walsh, and we should use this Grace code somehow, but we still, I think, don't understand how. And now we will try to understand. So here there is a main table that is explaining this intercorrespondence. In the first column of this table, we have number by Hadamard. This is a number of a horizontal row in the Hadamard matrix of 4th order. And we know that if we have order equal to 4, it means that we should change the number of rows and as well number of columns from 0 till 3, totally 4 numbers, 0, 1, 2, and 3. Okay, we do it. And also we construct a matrix of Hadamard. We know how to do this. Actually, we have a recursive algorithm. We have a rule how to construct the matrix of any dimension, any order. So we construct it for Hadamard, and we obtain a matrix H with a lower index 4. And the numbering of these rows is 0. First row has a number 0, second is number 1, then number 2, and then number 3. Here are these 4 values, 4 numbers. Then we should convert this number, we should consider it like these numbers like a decimal numbers and convert them into a binary system, just an ordinary traditional binary system. So we put instead 0, 0, 0, instead 1, 0, 1, then 1, 0, and 1, 1. Normal binary system. Only 2 digits because we have totally 4 values, so there is enough to use 2 digits. Then what we should do? We just should inverse of the order of this digit. So because we have only 2, so the lower digit become a higher one, and the higher become a lower one. So 0, 0 remains the same. 0, 1, it converts into 1, 0. The lower index, the lower digits is going to the highest place, and the higher digits is going to the lower place. And instead 1, 0, we are writing 0, 1, and 1, 1 remains the same. Then after this, after inverse ordering of digits, we should apply Gray's code. And you know that from previous slide, you know how to transform the normal binary sequence into the Gray's code. The main rule is that neighbor values should differ only in 1 digit. So we do it like here. The only thing that would be different, 2 things actually, 2 numbers will be different. So instead 0, 0 will be the same, 0, 0. Instead 0, 1, we should use 1, 1. Why? Because here we have instead 0, 1, 0, we should use 1, 1. So we put it from the previous table just here. And then we are doing conversion from the binary system to a decimal system, to back. And we obtain the values, decimal values, 0, 3, 1, and 2, that are the number of horizontal row in the matrix, but it will be another matrix where the rows are mixed. And here there is a rule how to mix them, and it will be the matrix of Walsh transform. And we will mark this matrix with the capital letter W. And W is the first letter of the last name Walsh. So we, in such a way, we obtain a Walsh matrix. Dimensions of this matrix will be the same, 4 by 4, but the rows will be mixed in comparison with the Hadamard matrix. So here there are these 2 matrices, and you can compare them between each other. You can see that first matrix remains the same, only once, here and here. And here it was the second row, 1 minus 1, 1 minus 1. It was the row with the number 1 in Hadamard matrix here, but it became the row with the number 3 in Walsh matrix, and in number 3 is the last. So 1 minus 1, 1 minus 1. And also all other rows are mixed in such a way according to this rule. So this table, it indicates the connection between Walsh and Hadamard transform. And here you can see the matrices for the dimension 8 by 8 for the Hadamard and the Walsh matrix. So H8 with a lower index 8 and W with a lower index 8. You can mark, you can note that the rows are the same, but again, they are mixed. with the same algorithm like it was in a previous slide, but the difference is it was already more than 4 values. There are 8 values, and we should add rows in this table. So our counting will start from 0 and finished by 8. And we should use in binary form not 2 but 3 binary digits. And then to do the same, just to inverse ordering, of digits, then transformation to Grace code, and then to obtain the number of the row in a Walsh matrix here. Here there is first 4 matrices, first 4 basic functions of Hadamard transform and of Walsh transform that are represented only first 4, not all of them, but only 4. And here, the last 2 slides, they are devoted to the Hadamard method. It's example number 2, and the initial signal x from n is the same as you can mark. It's 1, 2, 0, and 3. It's the same like it was in example 1 here in this presentation, where we used Walsh method. Original signal is the same, but the spectrum will be different because here our task is to find Hadamard spectrum, not Walsh, but Hadamard spectrum. And here we use the matrix H, and we know how to construct matrix H, Hadamard matrix of any arbitrary order. And we know that because our original function is consist of 4 digits, so our Hadamard function should consist 4 horizontal row, and it should have a dimension 4 by 4. So we just use it using recursive algorithm. It's very easy. And then we should find a spectrum. It's also easy. We just have to multiply our original function by this matrix, and don't forget to put multiplier 1 over 4. 4 is the number of values in the original function. As a result, we will obtain this, and then the spectrum digits will be 1.5 minus 1, 2, and 0.5. And if you compare this with the result of example 1, when we calculated Walsh spectrum, here example 1 solution, it's the slide number 9. So you can see that there are the same digits, but the order is different. Here in Walsh, for Walsh method, we had 1.5, 0, 0.5, and minus 1. But in Hadamard method, we had now we have another order, the same numbers, but in another order. And this method is also symmetrical, so we can use the same matrix to obtain original function by known spectra. So we just put the spectra together, all these 4 values, 1.5, then minus 1 here, 2 and 0.5, and we will obtain the same original function like it was in example actually number 1 and example number 2 also. So that's maybe all about this, but it is not only this presentation that I would like to present to you, because the next presentation that is called presentation number 4, it's also a little bit about the same method. Couple slides are about the same method. It's this presentation, I will upload it to Google Class today, but we will consider not all these slides. We will consider only just about the half, because you see that the topics that are considered here in this presentation, in this lection, is Walsh and Hadamard transform continued, so it's continuation of the same theories that we already considered. And then next topic we will not consider today. Discrete cosine transform will be for the next time. By the way, when we when we finish considering this, then we will go directly to the practical work number 2, because it is devoted to Walsh and Hadamard transform. So we will just consider all theoretical issues concerning to this, and then we will go to practice. Okay, here on the slide, couple slides will be about the features of Walsh transform, about some properties. I would not stop in details on these properties, just for your information. If you would like to learn more about this, you will be able to do this, because there are a lot of different sources about this method. It's very popular. It is not new method, so I think you would be able to find a huge amount of information. Okay, first feature is orthogonality, and this is the main feature actually for all spectral methods, because without orthogonality, any of spectral methods will not work. What does it mean not work? It means that if we will take some original signal and calculate a spectrum for this signal, and then if you will try to find the original signal again using the known spectra, and if it would be no orthogonality property, so it would be impossible. We will not, in any case, we will not obtain original function as it was. So the main thing that should be correct for any spectral method is orthogonality of the basic function. So the basic function of any spectral transform should be chosen, should be constructed in such a way that any pair of these functions should be orthogonal to each other. In a mathematical expression, it could be noted like here: the Walsh function with the number m and Walsh function with number n. When we multiply them step by step, digit by digit, it should be, this result of multiplication will be equal to 0 if there are different functions. So it means n not equal to m. If they are equal, so if you will take only one basic function and multiply it by itself, of course, the result will be not equal to 0. But only in this way. If we take two different systems, so the result of their multiplication will be 0. And also is the same like in continuous form, but as I said you before, we will deal mostly with the discrete function. So discrete signal processing is our main topic in this discipline. And here you can see the illustration, how this orthogonality feature works. If we will take a matrix, already you know how to construct a matrix of Walsh or Hadamard, but here this is a Walsh matrix with a dimension 4 by 4, and we will take, let's say it's second and fourth function. Here is a horizontal row that is in a rectangular frame of red color and blue color, and we will multiply it together. We will obtain a result that's equal to 0. Here it is. Yeah, here it is the result. It's equal to 0. You can check yourself just by multiplication each digit by the same digits in another row. So 1 multiplied by 1 plus 1 multiplied by minus 1, then minus 1 multiplied by 1, and then again minus 1 multiplied by minus 1. And we should add all this multiplication together. We will obtain 0, of course. Second feature is multiplicativity. Actually, in a simple words, this feature means that if we take two different functions and multiply them by each other, the result will be the third function. But anyway, it will be one of the functions that are already exist in our set. It will be not some any other or some different function. It will be something from the set that we already have. For example, the same matrix that we considered again, 4 by 4, and we take also the same rows, yeah, that is marked by rectangular frames of red and blue colors, and we should multiply them. But here it's very important. We have to use the operation of the adding by module 2, and you should remember what does it mean. We did it, we considered it last semester in the discipline theory of information. So for binary system, for binary numbers, there is like a special operation that is called operation by module 2. When we are doing plus by module 2, so 1 plus 1 will be always equal to 0. 0 plus 0 will be also equal to 0, and 0 plus 1 will be equal to 1. So the only difference between the traditional addition is situation when two values equal to 1. 1 plus 1, it's equal to 0. It's something like we do in traditional binary system, but in traditional system, 1 plus 1 should be equal to 1, 0. So it's like a transferring to a higher digit. But here, when we do addition by module 2, so we don't do this transition to a higher digit. We just consider only 1 digit and it equal to 0. So the number of rows here, the rows that is marked by red rectangular frame, is this number is 1, because we are starting from 0, 0, 1, 2, and 3. So we take the rows with the number 1 and 3. And 1 is 0, 1 in a binary system, and 3 is 1, 1 in a binary system. And we should add these two numbers by module 2. And the result will be 1, 0. And when after converting to decimal system, it will be equal to 2. It means that if we take this and this row and multiply them using operation by module 2, we will obtain the next that is in between these values with the number 2. Here there is number function with the number 1, function with the number 3, and the result function with the number 2. But also there is still in the set, in existing set of basic function. And here that is already was considered in presentation, in previous presentation, it's a recursive algorithm for the forming of Hadamard matrix. So we have elementary bricks, H1, then we can construct H2 using this elementary brick, and then H4, when we know H2, we can construct H4. It will be like here. And then using H4, we can construct H8, the matrix with dimension 8 by 8, and a common formula. So it was already considered, and then also, but just a little bit repetition for better understanding connection between Walsh and Hadamard transform for better memorizing. So each row of Hadamard matrix is a Walsh function. The only difference is ordering. And how to find the number of basic function by Walsh using the number of basic function by Hadamard. Here there is a rule. Grace code, what about reflective grace code, we already considered it. And here also 2-digit, 3-digit, and 4-digit grace code, reflective gray code. You can also see these imaginary lines that divide all the set of binary numbers by halves, and the table that explains how to obtain number of Walsh function, the last column, using the number of Hadamard function. At first we represent it in binary form, then we should exchange the places of the digits from lowest to highest, and then to transform them into a grace code, and then to transform from binary system to decimal system, and we obtain the numbering of Walsh function and the row of the rows in a Walsh matrix. Here is from H4 we obtain W4. Here is the numbering just at first and the last columns of this table from previous. And actually the last slide for today, it's about some generalization, some conclusions about spectral transform, because here we will finish with the Walsh and Hadamard method. Then we will strengthen our skills by executing the practical task number 2, but not today. And here, just a generalization about the different spectral transform, not only Walsh and Hadamard transform, but also Fourier, but also Hartley, but also other spectral methods that we didn't consider, but you should know that there are a plenty of different methods of spectral analysis that could be, and actually that are used, and that are very popular and well known, and also gives very good results. Of course, we are not able to consider all of them, but we consider some of them, and I hope it will be effective for you and useful if you would like in the future to use some of this method when you will deal with some task of signal processing. So fields of application, of course, there is not a full list, but just an examples where it could be used, where it could be applied. It's like a calculation of convolution and correlation. I already told you about the convolution function. It's like a method that we use in electronics and electrical engineering for calculating and for analysis of transient and steady state processes in electronic schemes. As regards to correlation, it's like a task of the defining of similarity between some processes or some signals. So how similar is one signal to another one, and how much they are similar, or they are the same, or they are opposite, or they are not similar and not know any connection between each other. It's all the task of correlation. Estimation of transient and steady processes, I told you already. Then spectral analysis itself, it could be different application. For example, if you use Fourier, it could be frequency analysis. So we should analyze what is the share of high frequency components or middle or low frequency components in the spectrum of signal. And because of this conclusion, we can analyze the signal and also to control some system or some processes. Then also very important application is data compressing, because sometimes there are a lot of data and a lot of let's say binary digits that we have to use in order to memorize this data. So the volume of the memory that should be used to store some data, it could be images, it could be some complicated signal, whatever. So the very actual problem is how to compress the data, how to decrease the size of necessary memory in order to store the data, but to use a less memory for this. And also it could be used in different fields, because the data could have a different nature. It could be medical data, acoustic data, electronics data, electrical, and so on and so on. And also interesting application, it's a template recognition, when we have to compare something with some example, with some template, and to understand how this signal that we would like to analyze is similar to the template. It's like a task of diagnostics, and it could be not only medical diagnostics, but also the diagnostic of the state of technical devices and so on. So these are not full, but just an illustrating list of possible fields of application. Okay, so the next slide in this presentation will be about data compression, and then we will go to the next method that is called discrete cosine transform. But it will be next time. So for today, that's it. And I thank you for the attention, and I'm just stop my recording.